Right, in this session, we're going to briefly look over how to do calculations involving gas volumes. Okay, so first of all, let's go to a few principles behind the relationships we'll be looking at later on. First point, gas particles can be very different in size. So, for example, both of these particles are gas particles. On the left, we've got a helium atom, and on the right, we've got an ethene molecule. Both gaseous substances, and you can see that the helium atom is going to fit many times over into the ethene molecule in terms of the size. However, the thing to understand about gases is that gas particles are very, very, very far apart. So much that that the space between the particles is much more significant than the size of the particles themselves. So if we zoom out, looking at a sample of helium gas and ethene gas, what you will essentially see is that there are about the same number of particles in the same volume, or, well, in fact, pretty much exactly the same number of particles within the same volume. So within boxes of the same size, you will see that you will have 6 helium atoms or 6 ethene molecules. Now, this, of course, is only holds true so long as the gases are at the same pressure and the same temperature. Okay, if the temperature and pressure are different, then you can possibly have a different number of gas particles within a certain volume. But so long as the temperature and pressure are the same, there are always the same number of gas particles within the same volume, and that's completely independent of what gas it is. Okay, so if I've got 1 decimeter cubed of a particular gas, there is always going to be the same number of particles in that 1 decimeter cubed so long as I've got a gas and so long as we're dealing with the same temperature and pressure. Okay, so this means that at the same temperature and pressure, 1 mole of a gas always occupies the same volume. This is called the molar volume for gases, and it can be measured. We mostly work under 1 atmosphere of pressure and at 20 degrees Celsius or room temperature. Under these conditions, a gas occupies 24 decimeters cubed or 24,000 centimeters cubed. And this relationship can be put into a helpful equation. So this volume here is known as the molar volume of a gas. Okay, if you've got any quantity referred to as the molar quantity, that just means how much per a mole. So molar gas volume is the volume of 1 mole of a gas. You might also hear the term molar mass of a substance. That is how much 1 mole of that substance will weigh in grams. Okay, right, and for any gas, the molar gas volume is the same, so long as we're at 20 degrees Celsius and 1 atmosphere of pressure. Now we can put this relationship into an equation. So the number of moles of gas is equal to the volume in decimeters cubed divided by 24, or it's equal to the volume in centimeters cubed divided by 24,000. Either of those calculations will give you the same output. Okay, so let's have a look at a few examples for these calculations. So number 1, volume occupied by 2 moles of carbon dioxide. So the molar volume of a gas is 24 dm cubed. And because we've got 2 moles, we're going to times that by 2. So we're going to have 48 decimeters cubed of carbon dioxide in this case. The number of moles of O2 in 240 centimeters cubed. Well, from the equation over on the other side, we know that the molar volume of a gas is divided by, from the equation over on the other side, we know the volume of a gas divided by the molar volume will give us the number of moles, but we have to be consistent with our units. So if we have a volume in decimeters cubed, we divide by 24 decimeters cubed, which is the molar volume in decimeters cubed. If we've got a volume in centimeters cubed, we do the volume divided by 24,000 centimeters cubed. which is the molar volume in centimeters cubed. So we can say moles in this case is going to be equal to 240 divided by 24,000, which is going to give us 0.01 moles. Okay, I think that should be correct. Volume occupied by 5 grams of methane. Now this is more complex because we have a mass of methane rather than the number of moles. So the first step is to find the number of moles, and moles is equal to mass over mR. Mass is going to be 5 grams, and the mR of methane, which is CH4, is going to be 12 plus 4, or 16. So you're doing 5 over 16, which gives us 0.3125 moles, and then the volume is going to be equal to the number of moles times by the molar volume, so 0.3125 multiplied by 24 dm cubed, which gives us 7.5 decimeters cubed. And lastly, the mass of 40 litres of hydrogen. So 40 litres of hydrogen, first thing that we need to do is find the number of moles of that. Now 1 litre is the same as 1 decimeter cubed. This is a handy little conversion to be aware of. So we have 40 decimeters cubed here. Right. 40 litres of hydrogen, well, we're going to do 40 divided by the molar volume, so the volume we have divided by the volume of 1 mole. That gives us 1.67 moles of hydrogen, and this is going to, of course, be H2. The mR of H2 is just going to be 2, and therefore the mass equals moles times mR, so that's going to be 1.67 times by 2, which is going to be 3.33 grams. Okay, so of course these conversions, these are all relatively simple because you're always dealing with the same conversion. It's completely independent of what sort of gas you've got. The volume being converted into moles is the same for any gas. If you, however, start off with masses, or you want to find masses at the end, you do have to do a calculation with MR in order to find the number of moles or to find the mass at the end, as we've seen in the last 2 examples. These calculations can be featured as part of a general reaction calculation. So for example, you could have a difficult worked example where you are told, for example, magnesium is reacting with hydrochloric acid. The hydrochloric acid is in excess and you have 12 grams of magnesium. Calculate the volume of hydrogen gas that's going to be produced. And your basic layout would be the same. First of all, find the number of moles of magnesium. Then use the balanced equation to find the number of moles of hydrogen that could be produced. But then rather than converting moles back into mass, here you would convert moles into volume using the equation that we've seen earlier. So volume is going to be equal to moles of gas times 24 decimeters cubed, and that would then give you your volume of hydrogen produced.